university physics lab. So for the mm, first optics in optics lab, you can easily observe the how the spectrum is going to be getting. That means whenever you are using a mercury vapor lamp here, it is going to be incident upon the prism directly. You can able to see that white light which is going to be dividing into 7 colors. That means you need to know that here the white light which may includes the combination of the 7 colors. If you say that 7 colors means different wavelength, okay, 4000 to nearly 7000 Armstrongs. So that here you can able to get the here seven different colors. That means each and every color have its own wavelength, or else you have to say that frequency. So that means what are the 7 colors? VIBGYOR: violet, indigo, blue, yellow, orange, red, green, red, like that. Okay. So for red color is wavelength is more here, nearly 692, 64, 65 to 7000 Armstrongs. 1 Armstrong is 10 power minus 8 centimeters here. And for violet 4000, nearly 392, 4000 Armstrongs. So you can able to see that here the spectrum. So that for a different colors which is going to be giving out. So what is the figure here? Apparatus to measure the atomic spectra. So for a one atomic atom, how the spectrum is going to be giving out, where S1 is a slit here, P is the prism, and PP is the photographic plate. So the spectrum which is going to be capturing on the photographic plate. And what is FPP? Front view of photographic plate. So you can see here like that the spectrum, line spectra which is going to be giving out. So we just want to see that here. So the source which consists of an electric discharge which is passing through a region containing a monoatomic gas. Okay, source is a monoatomic gas. Mono means only single. Okay, so because of the collisions in the atom, so when gas means gas which may include the molecules or the atoms, there should be collisions is going to be takes place here. So with the electrons and other atoms, some of the atoms discharge you may go into the energy which is higher than the here energy which may possessed by the atom in the normal state here. So that here the normal energy, these give up into the excess energy emitting the electromagnetic radiation. So like that the radiation which is going to be giving out after radiation which is passing through the collimation. So by the slit which is passing through the prism, and so that that light which may be divided into 7 colors which may be recorded in a photographic plate. So that here how the electromagnetic radiation which is going to be emitted by the free atoms you can easily find out. So for this here which may be giving a number of discrete wavelengths here, not in a continuous. So that you can, where discrete means each and every line have its own wavelength here. So lines are there now. So that for each and every line you can have its own wavelength here. So that is the discrete wavelength here, not in a continuous here. Okay, Nandi? So the spectra which is going to be emitted by the different kinds of atom which is located in the atom which has own characteristic spectrum. So many experiments which have been performed for the alkali metals and how the spectrum which is going to be giving out. So for particularly for hydrogen atom, you can see here for hydrogen atom, visible hydrogen atom. See here. Okay, for one molecule, how the spectrum which is going to be giving out here. H alpha, what is the wavelength here? 6562 Armstrong, and H beta 4561, H gamma, H delta, HS up to H infinity. Okay, between the H alpha to H beta, there is a nearly 2000 Armstrong difference is there. So like that, and H infinity, which is it comes into the, if you are going to be observing the spectra, okay, IR between the visible region, IR and ultraviolet region is there. So like that, ultraviolet region which comes into the H infinity. So this is the visible part of the hydrogen spectra here. Next, how the spacing is going to be takes place here. So how to calculate the Rydberg constant? Next, Bohr's theory. You can see here. In 1913, Niels Bohr, he has been proposed a theory of the hydrogen atom, and based on this explanation of the what is the here that means here different wavelengths have its own series here, like that Balmer, Passion, Bracket, Fund. Okay, so here Bohr has been proposed the what are the postulates here. So here an electron in an atom, most important, that means here Bohr's theory. So an electron in an atom which can move in a circular orbit about the nucleus. So under the influence of the Coulomb's attractive force, so between the electron and the nucleus, electron have a negative charge, nucleus is a positive charge. Nucleus which contains the nucleons, those are the protons and neutrons. Proton is a positive charge, nucleus is a chargeless particle. So that easily you have to imagine that nucleus is a positive charge. So in different orbit, the electron which is going to be revolve around the nucleus. So which is going to be obeys the laws of classical mechanics. Later on, instead of the infinity of the orbit, so which is possible to the classical mechanics. So it is going to be assuming that electron moves in an orbit, and where the angular momentum you have to say that capital L, and which is an integral multiple of h by 2 pi. H is a Planck's constant here, 6.623 into 10 power minus 34 joules second. So angular momentum, which is going to be here an integral multiple of h by 2 pi. Next, the electron constantly accelerating, an electron moving in a such allowed orbit, and which does not radiate the electromagnetic energy, so that the energy which is going to be remains constant. So and also these allowed orbits you can call it as a stationary orbit. What do you say? Stationary orbit. Next, electromagnetic energy emitted if an electron. So initially which is going to be moving in orbit, total energy, and that is EI, and discontinuously changes the motion, which is going to be moves an orbit of total energy E gamma. So in our formal language, you have to say that the final energy minus initial energy, EF minus EI. Okay. So divided by H here, radiated emitted energy. Why? Because of delta equals to EF minus EI, that is H nu. So frequency you can call it as nu equals to EF minus EI by H. But here they have been written that EI minus E gamma. So final. So like that here, when the emission is going to be takes place, when the here absorption is going to be takes place, that is based on this. And also here, what is the fourth postulate, which is closer to the Einstein postulate? That means here the frequency of a quantum of electromagnetic radiation, which is equals to the energy radiated by the quantum divided by the Planck's constant. That is the written here in previously. So here, but what are the failures they have been considered by the Bohr's postulates? So we will discuss, but the thing is that you need to read out that here the equation part. So which is very, very important here. You have to consider that nucleus, that is the charge of the nucleus is Ze, and mass is m here. The single electron, hydrogen is a single electron, only one s1, only one electron is there. So the charge of the electron is a negative. So that here you need to say that you need to draw this according to the mechanical stability of the electron, Coulomb's attractive force. Okay, Coulomb's attractive force means here, what is that? Coulomb's attractive force. When two charges are going to be separated by such a distance here, Q1 and Q2, which are separated by a distance small r, so the force of attraction or repulsion, which is always proportional to the product of the magnitude of the product of the charges, and also inversely proportional to the square of the distance between them. That is F is proportional to Q1, Q2 and inversely proportional to 1 by R square by combining Q1, Q2 by R square. So like that here, what is Q1 here? ZE and Q2 is minus E. Like that you have to imagine. So based on that, the equation is going to be comes out here. Under this, there should be here centrifugal force which is equals to mv square by r. So left side is also f, right side is also f here. So that by equating the equations which is going to be coming out here, k naught, which is in our formal language you have to write it down epsilon naught. Okay, so that value is 9 into 10 power 9 Newton meter square per Coulomb square. So simply I have to say that there should be f is there. Okay, charges are there. That's why written here epsilon naught value. So ZE square by R square equals to MA square by R. By doing the calculation and angular momentum value, L equals to MVR, that should be equals to the, according to the Bohr's postulate, second postulate, okay, h by 2 pi and h by 2 pi. That value should be h cross. So you need to remember that what is the h cross equals to h by 2 pi. So by simplifying this equation, you will get the what is the radius of the orbit here. Later on, you need to find out that what is the velocity, okay, and what is the energy, how the energy which is going to be quantized here. And you need to, if you want to calculate the energy, you need to find out that what is the potential energy. Some textbook they have written here U, and but here V. V is the potential energy, okay. Later on, kinetic energy, that is T of mu square. So that what is the total energy? The sum of the potential and kinetic energy. So by doing that, you will get the what is the energy which is going to be quantized, okay, of this electron, which is related to the hydrogen atom. Getting my point? And also Rydberg constant, R value. So what is the ground state energy level diagram? Most important energy level diagram. What is the ground state energy of the hydrogen atom? Okay, and first energy level, second energy level, like that you need to follow. And also you need to calculate the here Rydberg constant values. But here let me say you, so yeah, when the electron which is going to be emitting the energy, that means first you will get Lyman, and later on n equals to 2, nf equals to 2. So that the second energy level, that is a Balmer series, then Paschen, bracket, fund, like that, n equals to 1 2 3 4, like that. This is the equation here, okay. So simply you have to say that k equals to r into r is the Rydberg constant, 1 by nf square minus 1 by ni square. ఓకేనండి, కొన్ని టెక్స్ట్ బుక్ లోనేమో ఇట్లా రాస్తుంటాడు, ఇదేమో ఎన్ఎఫ్ మీన్స్ ఫైనల్ వాల్యూ 1 2 3 4 లైక్ దట్. మనం ఇక్కడ సబ్స్టిట్యూట్ చేసుకుంటూ పోతే ఇన్ విచ్ సిరీస్ ద హైడ్రోజన్ స్పెక్ట్రా, ఇన్ హౌ ద స్పెక్ట్రమ్ ఈస్ గోయింగ్ టు బి గివింగ్ అవుట్ ఫర్ ద డిఫరెంట్ సిరీసెస్. So that you need to understand that nf equals to 1 means Lyman series, nf equals to 2, Balmer, Paschen, bracket, fund, up to 5. So like that here the energy level diagram of the hydrogen atom you can see here. See here, for n equals to 1, so Lyman, n equals to 2, B is the Balmer, then Paschen, bracket, fund, like that. So this is the energy level of the hydrogen atom. Okay, most important question. Later on, Sommerfeld comes into the picture here, and according to the Bohr's theory here, hydrogen spectral lines which have been well defined wavelength, and also how but experiment with high resolution spectrographs which is going to be showing that H alpha, H beta, and also H gamma, which consists of several very closed lines which are packed together. And later on, Michelson, he has been found that H alpha line consists of two closed components. Okay, two closed components, okay? Close wavelengths which are closed. close, very close to each other for the H alpha. So that means the H alpha means 6,000, nearly 65,000 Armstrongs, 65,000 Armstrongs here. So there they have been observed that, and also which are going to be separated. The wavelength difference is 0.013 Armstrong. So which are known as a fine structure of spectral lines, and which could not be explained. But Bohr is said that only line spectra for different wavelengths which are going to be giving out for only one molecule. But when the Sommerfeld enter into the picture here, but when he is going to be focused on the hydrogen spectra for H alpha line, there closely two lines are there for different. What is the difference is there? 0.013 Armstrong. But he could not explain why these lines are going to be coming out closely. Okay, Bohr's. So that means that theory, Bohr's theory, is failed to explain about that. So that here the fine structure of spectral lines could not be explained by the Bohr's theory. So later on, Sommerfeld gave the two modifications. That means the electron revolve around the nucleus in elliptical orbit, not in a circular. Bohr said that only circular. వృత్తాకారంలో తిరుగుతుందని బోర్ చెప్పినాడు. బట్ సోమర్ఫీల్డ్ ఏం చెప్తున్నాడు? వృత్తాకారం కాదురా బాబు, ఎలిప్టికల్ ఆర్బిట్ లో తిరుగుతుందని చెప్తాడు. ఓకే, సో ద సర్క్యులర్ ఆర్బిట్స్ ఆఫ్ బోర్ is a special case of this. Next is that the velocity of the electron which is going to be moving in elliptical orbit, which can varies considerably at different parts of the orbit. Okay, so the velocity which is going to be changing here, so this causes the relativistic variations of the mass of the moving electron. So that this you can call it as a relativistic model of the atom. So here, according to the Bohr's consideration here, the momentum is also going to be associated with the two quantities which are to be quantized. That is integral p phi d phi equals to n phi h and p r d r and nrh. So n phi and nr, which are going to be known as here azimuthal and radial quantum numbers. And azimuthal quantum number you can call it as a angular quantum number, and which is also take it as a positive integer, and the sum should be equals to n, so that n is a principal quantum number. Okay, so like that, by doing these calculations, so is going to be getting that here how the explanations which is going to be given by the Sommerfeld. So you need to know that here he has been also calculated the what is the value of the azimuthal quantum number, and later on here principal quantum number, and he has been find out the what is the energy, total energy value. Okay, like that. The electron in the orbit of the principal quantum number, you know that small n, and he has been made a correction here, that is the term n phi. So depends on n phi, which is represent the Sommerfeld relativistic correction here, so that the correction which can gives the splitting of the energy levels of the atom, which is corresponded to the n permitted values of n phi. So here what is the energy levels of hydrogen atom? So you need to know that. See here energy levels of the hydrogen atom. So first to the second, like that here. Next is the vector atomic model. So in this vector atomic model, you need to know that here spatial quantization, spinning of electron, and what is the principal quantum number here, n, orbital quantum number, L values, how it is going to be changing here. If what it is going to be saying here, and also spin quantum number. Okay, square root of s into s plus 1 h by 2 pi, and total angular momentum value, that is J equals to L plus L, uh, uh, and the magnetic orbital quantum number, magnetic spin quantum number, ms values, mj values. So how it is going to be quantized, that is to be discussed. Only the thing is that here you need to know that the wavelengths of the atomic spectra, which can be representing the form of the empirical formula, so that for hydrogen atom and Balmer series, how it is going to be representing, and nu equals to 1 by lambda into r into 1 by nf square minus ni square values. And what are the Rydberg constant values? What are the Bohr's postulates in this? And later on, vector atomic and here Sommerfield's theory. So how in what case the energy which is going to be quantized here, when the emission is going to be takes place, when the absorption is going to be takes place, you need to know that. So all these cases, so then only it is easy to understand the concept here. uh, and the questions in this year, uh, Bohr's Bohr's theory and the vector atomic model, and also Frank Hedge experiment. So in this first unit, and that means the first block, we can have these questions. So be thoroughly prepared. And also here, when what condition you are getting the Lyman series, Balmer, Passion, bracket, Pandic here, how the variations which is going to be giving it. So we need to understand all these things here. Then only which is very easy to remember the